Hello, thank you for attending today's lecture, whether face-to-face or virtually. I apologise that I'm unable to attend in person today, but hopefully I can still deliver an interesting talk for you. My name's Dr. Chloe Leach, and I'm a Research Fellow at the University of Melbourne. My primary research interests are in the fields of coastal geomorphology and numerical modelling. In this talk, I want to talk briefly about what the coastal system is and how it changes through time. This will set the context for introducing the Victorian Coastal Monitoring Program that I am involved with through my position at the university. My role within this project is the lead numerical modeller, so I'll then take you through what numerical modelling is and how I have applied it to the Victorian coast. I'll then provide a short summary, and at the end I'll open the floor for discussion and questions. The coast is one of the most intensely used environments on the planet. In Australia, more than 80% of people live within 50 kilometres of the coast. How the coast behaves and changes through time can therefore significantly affect a large proportion of our population. Some of the biggest challenges we face at the coast is the threat of erosion and flooding. A report conducted by the Intergovernmental Panel on Climate Change stated that globally, coastal beaches have experienced net erosion during the last century. Understanding where coastal hazards like flooding and erosion are occurring and how this manifests at particular sites can help us to manage these environments sustainably. For instance, this could be by installing defences or by relocating vulnerable infrastructure. We can begin to understand the behaviour and changes of a coastal system by looking at what we call the morphodynamic feedback loop. This loop describes the interaction between sediment and water in the coastal system. The term morphodynamics describes the process by which the motion of water, what we term the hydrodynamics, moves sediment, and this changes the shape and form of the beach, or what we call its morphology. In turn, the morphology or the shape of the beach then affects the motion of the water, and the feedback loop continues. Take this as an example. I took this photograph along the coast where I used to live back in the UK. On this particular day, it was extremely windy, which caused strong destructive waves to lap against the coast. These are the hydrodynamic forcings that I mentioned previously. You can see how murky the wave is in the front of this image, and that's been caused by the high energy waves picking up and moving sand, so you can actually see that's the sand within the water. By moving sand, we get sediment transport. And with that sediment transport, this changes the morphology or the shape of the beach. So if I was to show you a picture of this beach before and after this high energy event, you might see that the beach has been eroded and is lower than what it was prior to the event. And as the shape of the beach changes, it can change how the water flows across it. So that's our morphodynamic feedback loop, the interaction between the water and the sediment. Now, there are many things which can affect the interaction between the sand and the water, and I'm going to pick a few things out of this photograph here. The first thing that I note from this image is the characteristics of the water and of the sediment itself. We can see that the waves are quite energetic, so they are able to pick up more sediment and move it around compared to when the conditions are calmer. The energy of the waves therefore affects how much sediment is moved. The waves are also coming in at an angle to the coast, which will drive sediment transport along the coast. This happens because the waves will carry sediment at an angle to the beach, but return to the sea at a perpendicular angle. This creates a zigzag pattern of sediment transport, which moves sediment along the coast in the direction of approaching wave angle. So in this image, that would be from right to left. This process is what we call longshore drift. I can also see a headland in the distance, which tells me that the geology varies along this stretch of coastline. It suggests that the headland is made of a harder, less erodible sediment than what is in the foreground where I am standing taking the photograph. The interaction between fluid and sediment can therefore be affected by the type of geology, or how hard or how soft it is. one of the other things I would pick out here are the human interventions. There are a couple in this image, including a seawall and groins, both of which affect the sediment budget. The sediment budget refers to how much sediment is added or removed from a system. For instance, the groins trap sediment on the updrift side of the structure. So if we look back to our longshore drift diagram and add in a groin, we can see that it's going to interrupt the movement of sediment along this coastline. This increases the sediment supply on the updrift side of the groin, but it decreases it on the downdrift side. On the downdrift side, this can lead to sediment starvation, where a lot of that material which might have moved along the coast is stuck behind this structure, and this can lead to erosion. So there are many factors which affect how a coastal system changes through time, and these are just a few examples that I've picked out that affect that water and sediment interaction. Each coastal system will have its own unique combination of factors, and that's why we need to study lots of different coastal systems individually. So I just want to pause here before we move on to our next theme in this lecture. We've just talked about how coastal change occurs due to the interaction of sediment and water, and that there are a whole number of things that can affect these interactions, such as the presence of coastal structures, how energetic the wave climate is, or what the sand itself is like. So in the next 5 minutes, what I want you to do is have a think about this morphodynamic feedback loop that I've been talking about in a little more detail. If you're able to discuss in a group or with a partner, that's great, or feel free to work individually. What I'd like you to do is think of a coastal site you know well. Is there anything you can identify that might influence the nature of the interaction between sand and water at this site? How might these influences on the water-sand interaction affect how the coast changes through time? So to get you started, in the example I have just given on the previous slide, I talked about how the groins trap sediment, and whilst this causes coastal change on the updrift side by collecting sand, it causes erosion on the downdrift side since it is starved of the sand. Okay, so I'll give you 5 minutes to discuss. Time is up. I hope the discussion was useful, even if it just meant that you looked at the coast in a more of an analytical way than you might have done before. So now I want to move on to talk more specifically about the Victorian coast. The southern coast of Australia is considered to have one of the most energetic wave climates globally, but conditions do vary from west to east across the system. As you can see on this map here, conditions tend to be more energetic on the western side of the coast and less so on the eastern side. Understanding coastal processes that occur across this stretch of coastline and identifying hotspots of change, for instance by identifying areas of continued erosion, are necessary if we are to undertake informed coastal management. A broad assessment of hotspots of change was completed within the Victorian Coastal Monitoring Program. This is a project I'll introduce properly in a moment. So the results of this study were calculated using satellite imagery spanning a 31-year period from 1987 to 2017. Map A at the top shows all the locations where the shoreline has tended to prograde over this period, and Map B at the bottom shows locations where the shoreline has overall shown erosional behaviours. And you can see how they vary along the coast. The size of the circles is representative of the rate of change, with larger circles being greater rates of change, and the different colours are to identify the different environments from sandy beaches to rocky coasts. Following on from this broad-scale assessment, further monitoring of coastal behaviours and change along the Victorian coast has been enabled through the Victorian Coastal Monitoring Program. The programme was established in 2017 as a collaboration between the Department of Environment, Land, Water and Planning, the University of Melbourne and Deakin University. It was designed to improve coastal erosion monitoring and assessment along the energetic coast of Victoria. And there are 4 key themes within the open coast section of the programme, including investigating shoreline sediment dynamics, marine sediment dynamics, coastal compartment modelling and visualisation, and coastal UAV and citizen science. Some of these priority coastal compartments are shown here by the blue points. Included are places like Port Fairy, Apollo Bay and Inverloch. I've also included some photos here illustrating some of the data collection that we have already done across the state. This has included connecting wave climate data, sediment sampling onshore and offshore, and monitoring coastal change through our citizen science drone programme and through the CoastSnap project. To look at a couple of these examples in more detail, one of the large-scale projects that has been rolled out as part of the VCMP is the Wavebuoy network. It is the most comprehensive network that the state has ever had. There are currently 16 wavebuoys deployed, and the data can be viewed and downloaded from the link on the screen. On the website, you'll find time series of the wave height, wave direction and wave period for each of the 16 sites that span the entire state. As we saw at the start of this lecture, the wave climate is one of the important components of the morphodynamic feedback loop. Therefore, understanding the wave climate is vital for understanding sediment transport and for identifying coastal change. The Citizen Science Drone Programme has also been a staple project within the VCMP. Groups of volunteers at various priority coastal sites along the Victorian coast have been provided with drones and training in monitoring beach change. The drone footage that they collect is used to produce high-resolution 3D models of the coastal environment at approximately 6-week intervals. The time series of the models allows us to look at how the system is changing through time. We can also then associate changes we identify in the coastal system with other driving forces. For instance, we could look at what the wave climate was like during a period of significant change and try and identify the linkages between the sediment transport, changes in morphology, and the hydrodynamic conditions. Again, thinking back to our morphodynamic feedback loop. So far as a team, through all the different component parts of the VCMP, we've been able to use data like this to understand how the coastal environment behaves. We've had a lot of successes as a team, producing a number of scientific publications, receiving awards for our work, and being interviewed by the media about our research. But our greatest success is learning how our unique and dynamic environment behaves. My role within the Victorian Coastal Monitoring Program is as the lead numerical modeller. I principally use numerical modelling techniques in order to understand coastal behaviours in the priority compartments and look at how they might change in the future. So what I want to do now is take a little bit of time to step out and look at what modelling is, and then I'll circle back to how I'm using models within the Victorian Coastal Monitoring Program, and I'll include some work I've been doing in Port Fairy as well. So thinking about models, a model is simply a representation of reality. And with this broad definition, as you can imagine, a model can come in many different forms. Take something simple like an apple. Here are a whole set of images that are all showing different models of apples. They are all representing this item in some way, shape or form, but they're all very different. The level of detail is different. What's taken as the core thing that is being represented is different. The scales are different, and so forth. We use models throughout science to provide us with a simplification of reality, as I mentioned. This provides us with a way of exploring really complex things within data sets to explore theories or processes. And this ultimately helps us to improve our understanding of the processes or behaviours we are studying. And that helps us to answer our research questions. Through representing and exploring something in this way, we can also use the models in a predictive capacity. And there are different types of models out there. I'm going to very briefly talk about 3 common types we use in science. The first is a conceptual model, which uses concepts or ideas to represent reality. Here's an example of a conceptual model that you might recognise from physical geography. This is talking about the way we represent how sea level rise might affect the cross-shore coastal profile. But I'll come back to this a little bit later. We also have physical models that use an actual physical entity to represent reality. Take the example here of a sandbox. We are showing the topography of land or a beach using sand that is trapped within a box that we can move around. Or there are mathematical models that use equations to represent reality that are often solved in a computer program. And considering these 3 types of models, let's look at some examples. Each of the models that I'm going to show you are representing sea level rise. That is, the increase in level of the world's oceans due to global warming. For our conceptual model, I'm using the example of the Brun rule that I mentioned on the previous slide. Here we have a cross-section of the coast, with dry land on the right-hand side and the ocean on the left-hand side. In its most basic form, the Brun rule is a conceptual model that describes how this cross-sectional profile might respond to sea level rise. The rule states that as sea levels rise, the dry land will be eroded and move backwards, and the eroded material will be moved offshore to bring this part of the profile upwards. And what's really important here is not the theory per se or understanding the theory in detail, but it's just a demonstration of what a conceptual model is and how the coastal profile might respond to sea level rise through using this conceptual model. And here's an example of a physical model. This was built by Beal Science. You can follow the QR code at the bottom of the screen to watch their full video and find out more details. So this physical model is an augmented reality sandbox that uses a projector to allow you to look at the topography of the land. As you move the sand around, the contour lines move too, and there are many ways you can use this sandbox. So sticking with our theme, here they are putting tiny houses on the land and moving the sand around to raise the water level, and this is to simulate sea level rise. Again, this is a physical model that is representing sea level rise in a similar way to what the conceptual model was, just in a different type of modelling environment. And finally, numerical models. Here are some outputs of a model that I built to look at the effects of sea level rise on a coastal system. This model is called the Coastal Evolution Model 2D. If you imagine we are looking at a bird's eye view, the black is the sea, the grey is the beach. We have these tiny undulations along the shoreline at the interface between the beach and sea. When the simulation plays in a moment, the left image will show the evolution of the shoreline only affected by waves. The image of the right will show the same simulation, but with sea level rise as well. So as the simulation runs now, we can see that spits are created along the shoreline. They translate longshore due to that process of longshore sediment transport that we talked about previously. In the image on the right, we not only see the formation of these spits and their translation longshore, but we also see the shoreline moving backwards due to sea level rise. So this is a numerical way of representing that change in the coastal profile due to sea level rise. So there are our 3 examples of different types of modelling approaches you can use to tackle the same problem or question. And whilst we have shown that each of these are useful approaches, each have their individual advantages and disadvantages, and these need to be weighed up when you're deciding what type of model is suitable for your project. So in my research, I apply a numerical modelling approach. These types of models allow me to simulate and investigate longer time and space scales. They're efficient at doing so. You can reproduce the results or run combinations of simulations to test out different theories or research questions, and they're pretty cost effective. One site where I've applied numerical modelling to understand coastal processes is Port Fairy. You may all be familiar with this site, but I'm going to give a brief overview for those who are less familiar. East Beach in Port Fairy is a southeasterly facing sandy coastal system on the western side of the Victorian coast, and it is exposed to some of the most energetic wave conditions across the state of Victoria. East Beach has been subject to erosion since the 1870s, following the construction of the training walls at the entrance to the Moyne River at the southern end of the embayment. It has since undergone a series of management measures, including dredging of the Moyne River to maintain access for shipping after the installation of the training walls, installation of a basalt breakwater in 1910, a rock revetment in the 1950s, which has been extended and altered over time, and a series of timber groins built in the 1970s. But even though over 2 kilometres of East Beach is now protected to some extent by these structures, there are still unprotected areas that are reportedly receding at a rate of between 0.1 to 0.2 metres per year. The erosional behaviour of this system has been highly influenced by the management measures that I mentioned previously. For instance, the construction of the Moyne River training walls has reduced the sediment supply to East Beach. This is through both blocking transport through the Southwest Passage and by trapping sediment behind the walls at Lighthouse Beach. This effectively starved the sediment from East Beach, allowing it to erode. Another interesting phenomenon at East Beach is the influence of wave blocking. Port Fairy has an average southwesterly wave approach, but even as the waves refract into the bay, there is some wave blocking from Griffiths Island at the southern end of the system. The striped area shown in the southwest corner of the bay will be somewhat protected from the dominant wave approach compared to the northeastern section, and this is what we call wave blocking. We can see this effect in the diagram from some results I've been running with the numerical models. The darker colours show greater relative sediment transport rates, and the lighter colours show lesser relative sediment transport rates. Whilst this area to the southwest has lower sediment transport rates because it is within the wave shadow zone, this central area has high sediment transport rates. And having seen this, I was particularly interested in this wave blocking effect and how changes to the wave direction might affect the status quo in this area. So looking at some of the future predictions, it's been predicted that 29% of the world's coastline are likely to experience changes in the wave direction by 2100, On this map, blue areas represent negative rotations in the wave climate, and red areas positive rotations, up to plus or minus 10 degrees. However, little attention has been given to investigating the effects of this, with studies often focusing more on processes like sea level rise and how that affects the coastal system. With this in mind, I started to set up my numerical modelling experiment. The first thing I needed to think about was, what are my research questions? I wanted to know how the rotation of the wave climate might affect sediment transport in this coastal system in Port Fairy. I then needed to think about what process I was interested in representing. In this case, it's primarily the wave climate. I also needed to think about a suitable model to use, perhaps one that already exists, or I might need to build one. In fact, for this study, I used a model called Delft 3D. And once I had some of these key ideas in place, I started to design a series of simulations that I wanted to run. Because I was interested in the wave rotation, I designed an experiment where I ran a series of simulations one with normal conditions, and then some with plus or minus 10 degrees in the rotation of the wave climate. A positive rotation means the waves are coming from a more westerly direction, and a negative rotation meant that the waves were coming from a more southerly direction. And these were some of the results. So this map here shows the results of the normal wave conditions after 1 month of simulation. What I want to focus on here is that accretion occurred within Lighthouse Beach and erosion occurred around the tips of Griffiths Island. If you remember back to the start of this lecture, these are the sorts of behaviours we do know that occur in this system. I would like to take another break here so we can think about the research question before diving into the results. I would like you to get together in groups or pairs again for this activity, but feel free to work independently if you prefer or are tuning in remotely. In the next 5 minutes, I want you to think about some of the topics we've covered so far today, including perhaps the morphodynamic feedback loop and wave blocking processes. And I'd like you to discuss what you think the impact of wave direction change might be on this coastal system. Use what you already know about the baseline results that are being shown on the screen currently. Okay, I'm going to start the 5-minute timer now. Your time is up. I hope you had some really fruitful conversations. So let's now take a look at the results. As I mentioned before, under normal wave conditions, as we are currently showing on the screen, we have accretion occurring at Lighthouse Beach and erosion occurring at Griffiths Island. And we can see the different patterns emerging in these areas when we rotate the wave climate, either plus or minus 10 degrees. On the left, we have the more westerly wave approach, and on the right, a more southerly wave approach. This is where the explanation gets a little more complex, so bear with me. The colours on the maps in the middle, which shows results under normal wave conditions as I showed you previously, represents erosion in red and accretion in blue. The maps on the left and right hand side show differences in the amount of erosion or accretion compared to these normal conditions in the middle. The first thing to mention here is that regardless of the wave direction change, whether it's positive or negative rotation, Lighthouse Beach remains an accreting hotspot and Griffiths Island remained an erosional hotspot. Through the diagrams at the bottom of the page, I've tried to explain the colour coding for the maps with the rotated wave climates on the left and right hand side. So for an erosional hotspot, like Griffiths Island, if the map is showing a blue colour, it means that there has been less erosion occurring compared to under normal wave conditions. And if it is red, more erosion has occurred. For an accretionary hotspot, like Lighthouse Beach, blue means that more accretion has occurred compared to what occurs under a normal wave climate, and red means that less accretion has occurred. So let's take a look at Lighthouse Beach as our first example. In the baseline scenario, under normal wave conditions, Lighthouse Beach accretes, it collects sand. If we rotate the wave climate so it approaches from a more westerly direction, we have less accretion occurring in this area. If we have a more southerly wave approach, we have more accretion occurring in this area. In our second example, Griffiths Island is erosional under normal conditions. If we have a more westerly wave approach, we have less erosion occurring here. And if we have a southerly wave approach, we have more erosion occurring here. From both of these examples, we can conclude that where the wave angle is approaching from a more westerly wave direction, less change occurs in the system compared to normal conditions. However, if our waves are coming towards the beach from a more southerly direction, we are likely to see changes intensified in these specific areas. This may be because when we have a more westerly wave climate, there's more wave blocking occurring in this system. So firstly, you get less erosion around Griffiths Island, and then that supplies less sediment to Lighthouse Beach for its accretion. And the opposite is true for the other rotation. If you have a more southerly rotation, it exposes the coast more to the dominant driving wave conditions, so you get more erosion on Griffiths Island, and that provides more sediment for greater accretion within Lighthouse Beach. Having said that, at the beginning of this lecture, we talked about the fact that there are a large number of factors unique to every site that influences this relationship between fluid motion and sediment transport. This is a good exploratory modelling example where we have simply looked at the wave direction in isolation of other processes, but it would also be interesting to look at how other factors might influence these results, and this might be something that you want to think about after this lecture. So, where do we go from here? Through the Victorian Coastal Monitoring Program, we're continuing to monitor and predict likely changes in coastal systems through time and understand their morphodynamics. We're not only doing this using numerical modelling techniques like I've just shown you, but through a whole host of techniques. There is heaps more that we've been working on and that I'd like to show you, so please feel free to get in touch if you want to find out more about the programme. And we've covered quite a large area in this lecture today, so I just want to give a recap of some of the main themes to take away. We have shown that the coastal system is complex. It is a dynamic environment, and a large percentage of the world's population live within these zones. So it's important that we understand how they behave and change through time so that we can manage them sustainably. We can do this through projects like the Victorian Coastal Monitoring Program, which has strived to collect large amounts of data and monitor coastal change through time. I've gone into a little more detail about the use of models to understand coastal change, specifically numerical modeling that I've used as part of the VCMP. Having applied this technique to coastal compartments like Port Fairy, we can start to understand how sensitive these systems might be to changing environmental conditions, like changing wave directions. That's all I'm going to cover today, but if you have any questions, please feel free to contact me on the details at the bottom of the screen. And whilst unfortunately I can't answer any questions today, I'd like to open the room to questions and discussion. You may have all picked up different things throughout the lecture or have your own insights and knowledge to share with one another. And before I sign off, I'd just like to say thank you for inviting me along to speak today. I really hope it was interesting and insightful, and I look forward to meeting you at another time. Thank you.